this out.
A little,
If I click on the arrow,
and then down, and then
right,
just the little hump out to the side of it, halfway down.
halfway down. Oh, right there, I see it now. Thank you. Okay. So first of all, you can choose English or SI units and proceed by column. So in this first column, the first thing you have to do is calculate Y naught and Y sub C. And you see I've got these little boxes numbered step by step, 1, 2, 3, 4, 5. Okay, so let's say 1,000 CFS, and just put in the slope.
So if you're solving for Q, would you have to iterate within WSP?
Yes. Good point. Yeah, to construct the canal delivery curve, you have to iterate within WSP. So it's just a matter of changing input and pressing buttons. So let's do a trapezoidal channel, 30 feet wide with 41 side slopes, and magnings in of 1.025. Okay. So right away I see this is a mile slope with a normal depth of 5.7 feet and a critical depth of 2.8. Now we put in the channel length. Let's start with 1,000 feet. And the control depth. This is the boundary condition. To take into account that little problem I was telling you about for starting near, when you're starting at Y sub C, you can just put in a 0 and the program will do that for you. But, okay, so let's do that to begin. Let's make it a 0. And you click here, and so the program already tells you that what you should expect is an M2 profile. The length, the station is always the downstream end here. Right, that's 1,000 feet. So we're starting at the downstream end and computing in the upstream direction. And we approach within 99.5% of the, wait a minute, no we don't. Notice that the final depth here is 4.8 feet and I don't reach 5.7. So this is not, I have not reached a hydraulically long channel with 1,000 feet. In this case, 1,000 feet is hydraulically short because I don't reach the normal depth. And by the way, when you're computing when you're doing these problems with a reservoir, entering a channel, and you're iterating for the canal delivery curve, you're not iterating to get the depth equal to the reservoir level, but the specific energy. So capital H in the lake discharge problem is not the depth, it's the total head, which is the specific energy. So this is the number that you're iterating on right there, not here. Is everybody clear as to what I'm saying? If you haven't tried the problem yet, you might not be. Questions? Okay. And here's the momentum function that I told you that's being printed out. Okay. Now, if I were to make this channel 10,000 feet long, still an M2 profile, and notice that it still goes all the way to 0. Okay, so now you see it stopped before the full length. It stopped at x equals 9,800. And the stopping point was this 5.716, which is within 0.5% of 5.72. And so the length for it to be hydraulically long, if you use 0.5% as the plus or minus here, is 20,000, roughly, so it's about 10,000 feet. It's also useful to know these velocities and see how rapidly they're changing. Okay, so now what if I use, let's go back to, we don't need that long channel. So let's go back to, let's use a control depth of 1 foot. And the program detects that that has to be an M3 profile because the 1 foot is below critical depth right there. And so it starts at the boundary condition upstream. And now it goes, and it only takes 148 feet to reach the critical depth. See right there? 2.846. Again, within a certain percentage of the critical depth.
So you would compute that, so like if this were like the sluice gauge
Yeah.
that we're talking